The Gibbs free energy is defined as the enthalpy minus the temperature in Kelvin multiplied by the entropy. And here we apply it to chemical reactions. We're under a standard state. We put zeros here. And the standard state refers to pure substances or gases at a pressure of 1 atmosphere, or solutions with a 1 molar concentration. And for a chemical process where the reactants and products are present in the standard state, we take the Gibbs free energy change. So that's equal to the change in enthalpy minus the temperature by the change in entropy. And this measures whether a process proceeds without the input of external energy. So generally, nature moves towards low energy and high disorder states. So therefore, for an exothermic reaction, the change in enthalpy is less than 0, and where the products are more disordered than the reactants, the change in entropy will be greater than 0. We can use the standard Gibbs free energy change to determine if a chemical or physical process is thermodynamically favourable, or in other words, the process occurs without the input of external energy. And the condition for thermodynamic favourability is that the Gibbs free energy change is less than 0. Now historically, the word spontaneous was used, and that means the same thing as thermodynamically favoured. So for example, if we have a phase change from water to ice, well, we know that heat was lost. So therefore the change in standard enthalpy is less than 0 for an exothermic process. And when water turns to ice, it becomes more ordered. So the change in entropy is less than 0. And therefore this term is negative. And this term here is positive, because the entropy was less than 0. And therefore we say that this process is thermodynamically favoured at low temperatures, such that the Gibbs free energy change is less than 0. And this is true because water freezes at 0 degrees Celsius or 273 Kelvin. The standard Gibbs free energy change for a physical or chemical process, and typically we look at chemical reactions, is equal to the sum of the free energy change of formation of the products under standard conditions minus the free energy change of formation of the reactants under standard conditions. And the Gibbs free energy of formation is really the energy change due to the formation of 1 mole of a substance from its constituent elements under standard conditions. And this is typically at a temperature of 25 degrees. So given a chemical reaction, we simply subtract the free energy change of formation of the reactants from the free energy change of formation of the products. And these are already given in tables. So the energy of formation of molecules like hydrogen gas is 0 because they already exist in their standard state. And it doesn't take energy to form hydrogen gas from its constituent elements. Generally, we can calculate the free energy change of a process given a standard change in enthalpy and change in entropy. So for an exothermic process which has a positive change in entropy, then this term is negative, and this term here is positive. So subtracting these two, the free energy change is always going to be less than 0. And therefore the process is thermodynamically favoured for all temperatures. And if the process is exothermic and the change in entropy is negative, then this term becomes negative. So therefore for the free energy change to be less than 0, the temperature must be low. So the process is thermodynamically favoured for low temperatures because you have a negative value and then minus minus gives a plus. And I'll leave it for you to verify that for the following endothermic cases, this process is not thermodynamically favoured for any temperature, and this one is thermodynamically favoured for high temperatures only. So effectively for these two cases, we don't really need to do a calculation to determine thermodynamic favourability. Is the following reaction thermodynamically favoured under standard conditions? Well, we're given the standard Gibbs free energy of formation of the product, being ammonia. So the free energy change of the reaction is equal to the sum of the free energies of formation of the products. That would be 2 moles multiplied by minus 16.5 kilojoules per mole. And then minus those of the reactants. So we have 1 mole of nitrogen gas by the free energy of formation of nitrogen gas, and plus 3 moles of hydrogen by the standard free energy of formation of hydrogen gas. So the free energies of formation of the gases are 0, so we obtain minus 33 kilojoules because the moles cancel, and we can also write this per mole of reaction because you have 2 moles of ammonia per mole of reaction. So given that the standard Gibbs free energy change of the reaction is less than 0, then the reaction is thermodynamically favoured. Under which temperatures is the following exothermic reaction thermodynamically favoured? Well, given that the reaction is exothermic, the standard enthalpy of the reaction is less than 0. And given that we have 4 moles of gas on the left hand side and 2 moles on the right, then the standard change in entropy of the reaction is less than 0. So using the expression for the standard Gibbs free energy change of the reaction, we have the enthalpy of the reaction minus the temperature by the standard change in entropy. And given that these values are both negative, then what we get is negative minus a negative value, which will give us a negative value plus a positive value. And therefore, for the free energy change to remain less than 0, then this temperature must be low. So the reaction is thermodynamically favoured under low temperatures.